So we're going to start by talking about types of numbers. So our first type of number we'll talk about are called the natural numbers. The mathematical symbol we use to abbreviate the natural numbers is this N with the double bar in the middle. In our textbook, the natural numbers are defined as 0, 1, 2, 3, 4, basically the counting numbers including 0. In some other mathematics textbooks, the natural numbers are 1, 2, 3, no 0, and they define this set as the whole numbers. If you're looking at different math books, they're like, that's not what I remember from before. There's some discrepancy between mathematicians as to what the natural numbers are, whether it should include 0 or not. In the IB textbook and in IB land, it includes 0, just to be clear. If you do your college math course, it might. Probably won't. If you're a mathematics major in college, it probably won't. So examples of things that might not be a natural number. Can anybody give me a number that's not a natural number? Just shout them out. 0.2, excellent. Why is it not a natural number? Because it's not a whole number, right? It's got a decimal to it. What else? 7.6 for the same reason. Can someone give me another number that's not a natural number, but not because it's a decimal? Pi is still a decimal, though, right? -1. Why is that not a natural number? Because it's negative, right? So those are the kind of the two classic examples you could give, right? A negative or a decimal. Either one, not a natural number. The next set we'll talk about are the integers. The symbol we use to abbreviate the set of integers is the Z with the double bar in it. The integers include any negative or positive whole numbers and including 0. Sometimes if we want to talk about just the positive integers, we refer to that as Z plus. How is Z plus different than the natural numbers? It doesn't include 0. Very good. Remember, 0 is neither positive nor negative, right? So Z plus doesn't include 0. It's only the positives. Z minus, that's only the negatives. Again, doesn't include 0. Can someone give me an example of a number that's not an integer? Many examples given already would still work. 15.8, perfect, because it's not a whole number, positive or negative. That'll do. Everybody happy? Okay. Our next set of numbers that we'll talk about are the rational numbers. The rational numbers is anything that we can write as a fraction. When I say fraction, I mean it has to be an integer over an integer. So like 6.7 over 5.2 isn't written as an integer over an integer. But if I just multiply the top and bottom of that by 10, 67 over 52 is the same decimal. And now it is written as integer over integer and would count as a fraction or as a rational number. So the trick is, if I have a decimal representation, how can I tell if that's a rational number or not? Well, you're looking for two things. If your decimal terminates, like 15.8, we can write that as a rational number. It's not hard. You could just do 158 over 10, right? Easy enough to do that. The other is if the decimal repeats, like 0.3 with the bar over top is what fraction? 1/3. That is a rational number. So if we're looking for something that's not a rational number, we need a decimal that doesn't terminate and doesn't repeat. Example? There's several good ones. One of them's been mentioned already. You'd have used it all the time in geometry. Pi is the canonical answer here, yep. Other good examples would be E. You remember E when you did exponentials and logarithms last year? E is irrational, as well as many square roots, like the square root of 2, the square root of 3, not the square root of 4. Why not the square root of 4? That's just 2, right? And whole numbers are rational, right? How do I write 2 as a fraction? 2 over 1. Great. Is 0 rational? Well, 0 divided by 0 is not 0. In fact, that is something that's indeterminate. But 0 divided by 1 is 0. 0 divided by 2 is still 0. 0 divided by any non-zero number is still 0. So we can write 0 as a fraction. It is a rational number. Can't divide by 0. 0 in the denominator is the very bad one. Everybody cool? Our next set, are the real numbers. Again, we abbreviate the real numbers with the fancy R. Usually when I write it by hand, I just put like a double bar on the vertical. When I write the fancy Q for the rational numbers, I just put an extra like vertical bar inside the circle for my Q. The rational numbers is anything, any number you can write as a decimal. So pi, rational number. E, rational number. 7, rational number. 0, rational number. What's an example of something that's not, I'm sorry. I said rational. I meant the other R word. I meant real. Pi, real number. E, real number. 7, real number. What's an example of a non-real number? What's it got to have in it? It has to have an I in it. So like 3I or 5 plus 7I. Those are examples of non-real numbers. What do we call those kind of numbers? Well, like 7I is an imaginary number, but 3 plus 7I would be called a perfect complex number. That's the set of numbers that includes the reals and the imaginaries. Guess what, though? Not a part of this course. So we won't see any complex number things along the way. Which if you're like, oh, I don't remember much about that, it's okay, because it won't matter today. So as a visual representation here, the big circle is the real numbers. You can divide the real numbers into 2 chunks. There's the rational numbers and the irrational numbers. So there's the things that you can write as fractions and the things you can't. The things you can't are things like pi and e and the square root of 2. Inside of those things you can write as fraction, there's the integers, the positive, negative, whole numbers. Here, I stole this from a textbook where they were differentiating here they said the natural numbers didn't include 0. Sometimes we call the natural numbers plus 0 the whole numbers. Not in this textbook, but in many other textbooks that would be the case. And then inside of that is the natural numbers, so they like nest inside of one another. Interesting question here. Here, when we've drawn this, we've shown the rational numbers and irrational numbers look like they're the same size. You think that's the case? What do you think there's more of? They're not the same. There are more irrational numbers than there are rational numbers. Now, they're both infinitely many, but it's a bigger infinity for irrational than rational. Not something that's important for this course, just a bit of an aside. If you take enough mathematics course, we'll explain to you exactly like, how do you count bigger infinity? What does that mean? But that's, you take enough math courses, you'll find that out. I'm not going to spoil it today because it's beyond the scope of this course. And it's like yeah. Good news because I don't get it. And you don't need to. All right. Next thing to talk about in this first section is SI units. What are SI units? It's like your standard unit of measurement for like length or weight, right? So in your science classes, this should sound familiar, right? So in length, the SI unit is the meter. For mass, it's the kilogram. For time, it's seconds. Current, it's amperes or amps. Temperature is kelvins. Amount of your substance are moles. Light intensity is candelas. These are just examples. It's not something you need to memorize. But just reminding ourselves that, like, as a scientific and human community, we've agreed on certain standard ways of measuring quantities, because there's lots of different units that you could use to measure something, right? Temperature might be in Fahrenheit or Celsius or kelvins. Mass could be in pounds or kilograms. As an international community, we've agreed on certain ways of measuring these things. That's all this is saying, and just giving you some examples. Of this list, really the only two that might come as new might be electrical current and light intensity. Otherwise, I would think that your chemistry class or basic science class would have covered the other 4 or 5. Is that a fair assumption? So in terms of temperature conversion, again, we mentioned there's 3 ways typically we have to measure temperature: Kelvin, Celsius, and Fahrenheit. So to convert between Celsius, Kelvins to Celsius, you just subtract that 273.15. And in the same mention, if I wanted to convert Celsius to kelvins, we would be adding then 273.15. And then to go from Celsius to Fahrenheit, I'll take my temperature in Celsius, multiply it by 9/5, and then add 32. Or if I want to go the reverse direction, I'll take my temperature in Fahrenheit minus the 32 and then multiply by 5/9. None of these formulas are things I would expect you to memorize. They'd be given to you in any test or quiz setting. You just have to be able to use it. So you'd have to remember what the symbols meant, but no memorizing. In general, in this course, anything that you need formula-wise, you would be given. Almost no memorization. Is this okay so far? If there's questions or you're concerned, please stop and interrupt. It is okay. So again, with the metric units, the lovely part about the metric units is everything is on a base 10 scale. So we have, the prefix is milli, centi, deci, deca, hecto, kilo, that just represent, a 10-fold or a power of 10 factor of our base unit. And then we have some like derived units that are like a product or quotient of 2 different types of units. So if you're talking about area, that's the product of 2 linear distance units. So typically meters squared. Or volume is, like the product of 3 linear units. So like meters cubed. Speed or velocity is a rate. So it's going to be distance divided by time. So meters per second. Instead of writing it as divided by s, typically in our textbook, oh, that was it, huh? I went too long. We'll pick up where we left off next time. If you look, there's really nothing to do yet. None of the homework you can really get to yet. So don't worry about any of that. We'll see you guys tomorrow.